Hello friends, so today I will try to explain my solutions to problem A to E, A to F of AtCoder beginner contest. So let's start. So problem number A. You should read all the tasks on your own and obviously try them first. So in this question, what is given is, this is a pretty simple question. We are given n strings s1 to sn and we need to print them in reverse order, sn, s1 minus 1 and s1. If we are given a string abc and then bcd and cef, these three strings, then we have to print them in reverse order, this first, this, and then this. So we simply have to reverse the array. So we can read the array and print it in reverse order, and the array is an array of strings. So if we know how to take input and how to print output, how to run a for loop, then this is a simple question. Let me show you the summations pretty quick. So I simply read a vector of a string array A and print it in reverse order, n-1 to 0. This is a simple template. It runs a for loop in decreasing order. Coming on to the next question number B. Multi-test cases. We have multiple test cases in this question, that's why the name multi-test cases. In this question, in each test case we are given n positive integers, a1, a2, an, and we have to find how many of them are odd. So again, a simple question, we have to count the number of odd numbers among these. So we have to know how to check if a number is odd. So a number is odd if it is not divisible by 2, means if the number modulo 2 is not 0, then this is an odd number. So in this way we can check if a number is odd or not. So in this question simply we are given an array of size n, and we will simply loop over all the elements and count the number of odd elements by this condition. So let me quickly show you the code, my code. So what we did is, for each test case we are running this solve function on multiple test cases, and we read the number of elements and the array, and then simply do answer plus equal to this value x mod 2. If this x mod 2 can take two values, this can be either 1 or 2, means we know that any numbers mod, if we take modulo mod, then its range is from 0 to m-1. So if we check any number x modulo 2, then this will be either 0 or 1. If this is 0, then this is even number, and otherwise it's a odd number. So here I am doing answer plus equal to x mod 2. If this x mod 2 is 1, then this will add plus 1 to answer, and that's what we want, because we want to count the odd numbers. And if it is 0, then it will add 0. It won't make any difference. So in this way we can count the number of odd numbers. Okay, now the third question, count connected components. This is again a more simplest question of the graph. So means if you have a simple knowledge of graph and something, this is graph, then this is a most easy question. Okay, so we are given n vertices, like they are n vertices or n nodes, and we have given m edges, 1 to m. Each edge connects two vertices ui and vi, and we need to find the number of connected components. So you should read about what connected component means, the definition of connected component, and the basics of graph. Then this will be covered in every tutorial you will find. This will be covered. So we have to simply count the number of connected components. For this you can use any graph traversal algorithm like DFS, BFS, or DSU. Okay, so we have to count simply we have a simple and directed graph and count the number of connected components. I think you should read about graphs, the introduction to graph, so you will get this. So I have used DSU, disjoint set union, to count the number of connected components. For those who know how DSU works, so I will show you my code pretty quick. So I simply have a class for DSU and I take the n and m. Then for each of the edge, we take the edge ui and vi connecting x to y, and we merge this in our DSU, merge x y, and then we have to count the number of groups, number of components. So for this we can also maintain in our DSU. This we can also keep maintaining in our DSU, but I use a set and inserted the parent of each of the element, each of the group, parent of each of leader of every group, and this way I found the number of component. Coming on to next question, if we are given a positive integer n, it is known means it is definite, it is guaranteed that n can be represented as p square into q, where p and q are prime numbers. Okay, so n can be represented as in this form, where p and q are prime. We know that every number can be represented in its prime factorization, unique prime factorization, p prime 1 to the power something, p1 power alpha, p2 to the power alpha 2, and prime 2 to the power something, and so on. So our given integer n contains only two primes, p and q, in which its power, one of the prime powers is 2 and other prime is power 1. Okay, so how can we do this? So we have to find the two primes. Okay, so first of all, you have a basic idea of basics of number theory, like how can we factorize two numbers, factorize a number. So we know that every number, if we want to find all the prime numbers that divides a number, if we want to find all the prime numbers, then we can simply iterate only up to square root of n and find all the numbers which are divisible by n, because if d is a divisor of n, then other divisor is n by d. Okay, and simply these two values both cannot be greater than root n. If both of them are greater than root n, then the product will exceed n. Okay, but this product should be equal to n. So we can iterate on up to root n and find the other divisor. So in this question, our n is up to 9 into 10 to the power 18. So if we iterate on q, on one of the prime factor, like there are two prime factors, p square and q. If we iterate on one of them, p square or q, then we have to iterate up to square root of this, and this is 4.5 into 10 to the power 9, and this is this up to this extent we cannot iterate. So what can we do? So we have to see that this p square q it is. So basically it is kind of three prime factors, like p into q. Okay, so what we can observe that all of them cannot be greater than, let's say, 2e6 or 3e6 something. If all of them are greater than 3e6, then the product will exceed 9e18. So we can say that at least one of them is less than 3e6, means the minimum of this value is less than equal to 3e6. So we can iterate on up to 3e6, we can iterate easily. So let's first iterate by fixing q. If we iterate on q and we try q all the prime number, for q is a prime number, it is given. So if we try all the primes from 1 to 1e6, means or 3e6, all the primes are less than equal to 3e6, then we are fixing q, and the remaining part is n upon q. Okay, and this denotes our p square. Okay, so what I want to say is okay, sorry, right. second, guys. Let me erase this. Oh, sorry, this is written by this tool, not on our whiteboard, so we have to erase from here. I am new to this, so okay, right. So we have p square into q, and we know the minimum of them is less than equal to 26. So if we iterate on q less than equal to 36, we are iterating from trying all the q, means we are trying all the prime numbers which are less than 36. Then our remaining part is n upon p square. So if this is if this can be our n upon q is our remaining part, then we just check if this is a perfect square, then our p can be square root of n by q, and this will be our this is a possible answer. Okay, and we don't need to check if square root n by q is a prime number or not, because in the question it is given that it n can be represented. They are guaranteeing it that n can be represented as p square q, and since every number has a unique prime factorization, we don't need to worry about whether this is a prime or not, because if the answer exists, then it will be unique answer, only one answer will be there. So we tried all the q less than equal to 36. Now after that, q might be greater than 36, but if q is greater than 36, then this value, this p square, this has to be less than equal to around 312 or something, because if this is greater than 36, this has to be less than 312, because their product is 9018. Okay, so if 9018 upon 36, this is around 2e12, no, around 2.5 something, 2.3 something. So we will so this p square is less than equal to 312. Now we need to find p. Then this is an easy problem, because since this is p square and we need to find, we cannot iterate up to 312. This is also too much, but we are not iterating on p square, we will iterate on p, and then p can be only up to 2e6 or something. P can be only up to 2e6. So we will try all the p. From p we will find p. If we will check, we find p square, and the remaining part is n upon p square. And if this n upon p square is an integer, means this n is divisible by p square, and this remaining part is, we don't check if this is a prime number or not, because this is obviously be prime. If this is not a prime, then the question statement is wrong, because p is a prime, then p square is something, and if q is further divisible, then again you got my point that prime factorization is unique. So if q is further divisible, then the question is wrong. So okay, so in this way we will what the main idea is, we are iterating on q up to 36 less than equal to 36, and after that if q is greater than 36, that we know that p square is less than equal to 312. So in this way we reduced our problem. In this way now we can iterate on p, because p square is this, then p has to be less than equal to 2e6. Then we can iterate on p in this part and q in this part. Overall we are iterating 5e6 times, right? Let me show you the code. If you have any doubts, then please write your doubt in comments. I will definitely answer them. I have very rare subscriber. I will definitely answer. So for finding prime numbers, I am using sieve of Eratosthenes, so you can read about it. Using sieve we find the prime numbers. So in this part, so here we read n, and here I am trying all the q, iterating on q. So if we try all the prime numbers less than equal to 2e6 or 3e6, as we see, then obviously it should divide n, otherwise we continue. Then this is a possible candidate for q. Now the remaining part, as I said, remaining part is n upon q. Q is x here, n by x, and we found if this is a perfect square. If r is a perfect square, then we have found our p, and we simply output the answer. So how to check if this is a perfect square? we can find it as square root using its built-in square root function, but this is a can give little precision errors. Like if the answer is 4, then this can give 3.99999 something. Okay, and if the answer is 4, then it can also give 4 point, means you know that it can give slight precision errors. So for this we are typecasting to int also, so it will be, our answer will be plus minus 1. The error will be obviously of plus minus 1 error at most. So we are fixing that using this. While we are exceeding our answer, then before our answer we press, if we are exceeding, that we do s minus minus. So at this point our s into s value might not be exactly equal to the double value of square root of remaining, but it is the, you can say, the GIF of this value. Okay, so if this is a perfect square, then s into s is exactly equal to r. In that case, we simply print our answer. Our first integer p is s and our second integer q is x. We print this and return. Otherwise we are trying, now we know, now from this point onwards we know that p square, since q is greater than equal to 3e6, then p square has to be less than equal to 1e12, 2e12 something, 3e12 something. So in this way we see if n is divisible by x into x, because we are iterating on p, not on p square. We are iterating on p, so if n is divisible by p square, and then the remaining part is n upon x into x. Okay, obviously this will be divisible, because since this is a divisor, then the remaining divisor is also divisor. We simply output x and r, return from here. Okay, I hope you got the code. Right, the next question is counts simple paths. So here we are given a graph, undirected graph of n vertices and m edges, and we are given n vertices and m edges, and as I connect vertex ui and vi. I don't know how this is helpful. The degree of each vertex is at most 10. Degree of each vertex is at most 10. Why is this helpful? This has to be helpful. We will see how this is helpful. But let give me the number of simple paths. So let give me the number of simple paths starting from vertex 1. Okay, so everything has its usual definition. Like simple path is a path, they have written path without replacing vertices, means path in which the vertex are not repeated, say 1 2 3, then we can again not come to 2, or we can again not come to 1. Each vertex can occur at most one time. So we have to find the number of simple paths which are starting from 1, and we have to print the answer minimum of k comma 1 is 6. So this point we have to notice that if our answer is greater than, if the number of paths is greater than 1 is 6, we don't care, we simply print 1 is 6. Okay, so if we found our answer in one path in order one time, then then we can simply find all the paths naively one by one, and 1 is 6 is not very big. Okay, so this is the key point, 1 is 6 point. So we can simply traverse our graph, and each time we like in the recursive nature, we will, let's say starting from 1, we will try to go here on second node, then again we will try to go here, and then maybe we don't go here, maybe we go from 2 to 4 node. In this way we try to explore all the possible paths, and we see that every time we go to some node, let's say 5 here, then we have found one path, we have found one possible path, so we can increment our answer. So every time we are going somewhere, we are exploring one new path. We will make sure that we ensure one new path where we don't find any paths again and again. So we just have to implement this, so we can find all the paths in a recursive nature. How to find the path? This is a big question. How to find the path? So for this we have to know that what all nodes are visited. If we are iterated from 1 to up to, we are at a intermediate node I, intermediate node u. Then from 1 to u along the path we have visited multiple nodes. We cannot go back to them again. So we have to mark them visited. Now we will go from u to one of its neighbor which is not yet visited. Then from there onwards we will try to go somewhere. Okay. So we see that each time we traverse some edge, we will go traverse some edge when this node is unvisited, obviously, है ना. So each time we traverse our edge, we find one new answer, and then after exploring its complete path, we track back from here and try other possible paths. So this way we traverse every edge, we increment 1 to answer. So because of this condition, we can find answer in the time limit. Okay, so for this we have to know recursion and how to write recursive code. We have to simply we have to traverse the graph. Don't get stuck in a cycle. For this we keep a visited vector, because we can't go again to a visited vertex. That's why we have to keep a visited array. So the code looks like this. Here in this part I am simply reading the graph. Okay, and then now first of all, if we are calling this function go, if we are calling go of u, that this means what, that we have traversed some path from 1 2 3 up to u, and we are now at u. Now from u we can go to somewhere else. Okay, and in this visited array stores all the nodes which are currently visited in the path. So we mark one as visited and call its function go of 1. Okay. So if we see this go function, this is simply, so in this go function we are at u, so obviously we can end the path here. We have found one path from 1 to u, we are calling go of u, we can end our path on u, or we can continue to extend our path on, we can go to some other node. So if we end our path here, then we can do answer plus plus. Now if the answer is greater than 106, we can simply print the answer and exit from the whole code. This exit statement will exit the code, means not only end this function but also simply exit from the code. And we have written 0 here, so it exits normally with a success code. There is no failure, no error or something, so it exits successfully. We can also return false, true and something to exit from this function and then print here, but this is easier. Why is this coming in again? So now we try to go to one of the neighbor of u. For this we iterate in its adjacency list. This is the adjacency list of each node. Here for each node u, I am keeping a list of its neighbor v1, v2, v3, all the neighbors that you have. So if we are iterating on neighbor, and if the neighbor is already visited, then we don't need to go there, because we cannot repeat the vertex in a simple path. So if it is not visited, then we mark it visited and call its function, and call this go function. This will go there and try to find all the paths from there. And after we have explored this thing, from u we have gone to v. After we have explored, we will mark visited v0. It's visited as 0 because we are trying to explore other paths. Let's say we explored there, here. Then we can again come to v in this way. So that's why we have to mark this v as visited thing as 0, because in this visited array will only store the things which are currently in the path, from 1 to u. That's why when we come back from v, we have to set back the visited value to 0. Okay, this thing we do in backtracking, standard backtracking thing, that we try to do this. Let me explain. We try to, my god, we try to do things like put some one from, then go somewhere, and then not go here. Let's say try something from here. So we have to delete these things, because we are not trying this, we are trying this way. Okay, that's so from here we can learn one thing, that whenever we are doing recursion, then we are taking this global array visited. That doesn't matter. The main thing is whatever things which we have are currently in the recursive stack, whatever things we have which are currently in the recursive stack, let's say we are currently at 5, then we can keep some information about these elements which are currently in the recursive stack. So during recursion, if we are at 5, then we can easily keep some information, let's say the sum, or let's say some any information about the elements which are currently in our recursive stack, which are not yet, whose recursion is not yet completed. We have some options left here, some possibilities that we will try later here. So this is a key point. So in DFS also, let's say this is a general graph, but if we are doing a DFS on a tree or something, then if we are at some node, then we can keep information about the path from root to that node. We can keep any information about the path from root to that node. This is the number 1 point, and the number 2 point, we can obviously keep the information about some subtree, because each of our child will return some value of their subtrees, C1, C2, C3, and we can merge these value and calculate the answer for our subtree. Okay, very basic thing. So this way, since the condition given in the question of this one is 6, we are able to do this question. Next, let's see the last question that I was able to solve. Okay, let's read the question. So in this question, we are given a string s of length n, and they defined a function fi of s, which means we take the first I characters of s. Okay, we have this string s1, s2, sn, s1, s2, so on till sn. Now we take the first I characters of s, we are found, and then we append the reversal of string t. Means we are given this string s, and we are trying to form another string t from s of length 2n. This is of length n, this is of length 2n. So we take in s string t, we firstly append the first I characters s1, s2 up to si, and then we append the reverse of s. Reverse of s is what? sn minus 1 up till s1, and then we again append the remaining character from up to si. We have appended here last n minus I character, means from si plus 1 to sn. This we append, and this way we get our string t. Now we are given this string t, you are given this string t of length 2n, and we have to find some string s and some integer I. For which, if we perform this process sni with sni, then we get a string t. We are given t, we have to find some string s and the prefix length I, length of prefix I, using which fi of s equal to t. Okay, so for this question we need the knowledge about string algorithms. There are multiple string matching algorithms. Okay, let's come here. Okay, so what I mean by string matching algorithms, like those algorithms. Okay, so string matching, there are multiple algorithms to match the string. Like if there are two strings s and t, and we want to compare if these are equal or not, then if we naively compare this, then this will take time equal to their length. If its length is m, its length is n, then we have to iterate through them, and this will take min of n comma m time. But if we want to compare fast, then if we have compare fast and we have to compare many strings, like multiple strings, many substrings with each other, then we can take advantage of some of the properties of a string, that most of the substrings are overlapping. You see that most of the substring in a string are overlapping, so we can develop some algorithm which will compare these substring in an efficient manner. So for this we have many string matching algorithm. Like we can use hashing, but hashing is not deterministic, it can give wrong answers. Okay, and if we have many comparisons. Okay, next we can use prefix function like KMP algorithm, not Morris-Pratt, or we can use G function, and there are many other infinitely, not infinite, but there are many other algorithms as well. So we will use G function. We can also use prefix function. They are both kind of same. So what let me explain what G function allow us to do. Using G function, if we are given some string s1, s2, sn, then we can build an array, z array of size n, where for z of I, z of I represent what? Z of I represent the, if we start from I, then this substring I plus 1, the max length in which this substring is same as the prefix if we start from the beginning, s0, s1 up to si minus 1. So z of I is the maximum length of the substring starting from I, such that si up to si plus length minus 1 means the length string starting from I is same as the length string starting from 0, means the prefix. So this will give the max prefix which matches with this string. Okay, once again, if this is our string and we start at I, then z of I is max length L, such that this and this are same. Max L such that string starting from I going onward, this is same as this prefix starting from, prefix means starting from 0. This and this are same, so we have found gives the max length. Okay, so we will try to arrange our string in such a way that the string we want to match form our prefix, because G algorithm allows to match the any substring starting at somewhere with the prefix. So the pattern we want to match, should be the prefix. So we want to make our prefix some length of prefix of as our pattern, and we not this length, this prefix length is not fixed. This z of I will give that how much length of prefix is being matched. Okay, so again coming back to the question, in our question the given string is s1, s2, sn, and sn not a random arbitrary si, and then we have a reverse string sn up to sn minus 1 up to s1, and then again this remaining suffix si plus 1 to sn. So how we will do this? This is our given string t. Okay, so this is our t string. It has three parts like this some part is the starting I part, the some middle part is a reverse of string n, this is of length n, this is of length I, and this is of length n minus I. So if we will try all the prefix length, all the possible values of I is from 0 to n. Okay, so if we fix I, we know that this is of I, then we know that the next n characters are going to be the reverse of s, the next n characters, and the last n minus I characters will be the suffix of s, because total length is 2n. So how we will check? Let's say if we are at some I, so we need to quickly check what are these characters. These are s1 till si, and these are sn till s1, and these are si plus 1 till sn. So we need to check if if we are fixing I, then we need to check if this string, this middle part is correct or not, because if we know the middle part, then we know we can build our t. So we have to check if this s1 to si is same as this string. Means if we read from back here s1, s2, si, because we can easily get this its index, because if we are at index I, then its index is I plus n. Okay, now from I plus n, this is in reverse order, s1, s2, because this is s1 to sn. We have to check if the string of length I here is same as this string of length I. If this is same in reverse order, means same in reverse order, then this is correct. And also we have to check if this remaining suffix from I plus 1 to n, this is same as this part. These two, if we do these two comparison efficiently, compare this with this and compare this with this, then we know that this I is a good I, possible I, and we simply return our answer. This is our s, middle length, and string is our s, and this is our I. So how do we compare these two things efficiently? This is the whole question. How do we compare? So we need to notice that in G function we will keep the pattern we want to match in our prefix, and some random patterns in between. Okay, so we are given we have s1 up to si here, and sn till s1 here. Okay, so we can see that we want to match this s1 with this, then s2 with this, then s3 with this. But g function, we cannot directly apply g function here because this is in reverse order. This is the biggest bad thing, that this is in reverse order. Because okay, so what we can do is we can make another string, let's say another string, and in which we will take t and then add reverse of t, reverse the string t and then append it. So if we reverse the t, then this middle portion will be, this middle sn to s1 part will be again reversed, so this will become s1 to sn, right? This will be t, and this reverse of t, this s1 to sn part will be in right order, like s1 to sn. Okay, and this will be the prefix s1 to si, and this will be the suffix si plus 1 to sn. So now we can if we fix some I, then we have to check this I with these characters, but we will not check with these characters, we will check with these characters, because this is essentially the reverse of t na, this is the reverse of t, so this is same as this in reverse order. So we will check if this these characters s1 s2 si, these are same as this s1 s2 si here. Okay, if these are same, then well and good. So I think you understand the first comparison. I have said we have to make two comparisons. So for first comparison means, if for the part we have to check s1 s2 up to si, if we are fixing this I, then that means the next n characters are going to be our string s, the next n characters are going to be sn to si, sorry sn to s1, and then the last part is sn plus si plus 1 to sn. So how we will compare this with this? How we will compare this? We will make a string t plus reverse of t, and then using g function, so t plus reverse of t, how will that string look like? We will have s1 to si, then sn to s1, then si plus 1 to sn, and then since we are appending reverse of t, this will be, reverse means from the end, we will have s1 to si, then we have sn to s1, and then we have si plus 1 to sn. So we can see this s1 to sn part is in correct order, in right order, and this is also s1 to si is in right order. So we will, using g function, we will check this index, right? We know that this is the I index, so we can easily get this index, because this index is what? This index is 2n, because this string length is 2n, this string length of string t is 2n, we are appending reverse of t, this portion is reverse of t, so its index is 2n, and we know that this length is n minus I, so this index is 2n plus n minus I. So we will check z of 2n plus n minus I, and if the z function will give us what? This will give the maximum length is starting from here, which is same as the prefix length, the prefix of that length is same as this string. So we will simply check that the max length, that is z of this max length, is greater than equal to the required length, that is I plus 1, because if at least I plus 1 is matching, then these two are matching. If some more characters are matching, then good, but we just need to check if this length, if s1 s2 si is same as this, starting from here, is starting from this s1, we need to check the first I character. So for this we use the g function. Okay, next the second comparison. The second comparison is these s1 to si plus 1 to sn, this should match with this thing, but again the same problem. If we maintain a g function, let's say we build the g function starting from here, that we cut off this string and starting from here, then again this is in reverse order, this is in not in reverse order. So how will we compare this? So again we can use the same technique that we have used here. Okay, for this what we can do is, we can again do in this same string, we have this s1 to si, and we have we have this, let's erase this all. So for this, what I have did is, I have appended, we have given t s1 si, then sn s1 si plus 1 till sn, So for this, what we can do is we need to check these things. So if we so we can reverse t, we can make a string like reverse of t plus t. If you do this, then in reverse of t string, this will come at first, this will come first, this sn to si plus 1 thing, this will come first, and then s1 to sn, and then si to s1. So basically the main thing is that this will be reversed, this will be reversed, this sn to si portion is reversed, and then we have something, and we have something, and then we will adding plus t. So in this t portion we have s1 to si, and this portion is normally, this is not reverse, means this is in reverse form, sn to si, sn to s1. Now we can simply compare these last and minus I characters are same as these or not. Now we can directly compare using the same method that I have explained. We will check the z value of this index. If this is greater than or equal to n minus I, then good. What? Nice. So I think I have to show you code now. No. So this question was not very tough. If you have solved 3-4 questions of a string, then you can, not 3-4 exactly, but if you have seen this type of questions before. Yep. So here I am simply reading the input, reading NNS, and then making this string that I have explained earlier. In the first comparison, I am making the string t plus reverse of t, plus reverse of t. So how will that string look like? The string t is s1 to s1 to si, and then sn to s1, then si plus 1 to sn, and the reverse of t will be how? Reverse of t will be like sn to si plus 1, and then this part will be not reverse, this part will be correct and incorrect order, s1 to sn and si to s1. So we are interested in this portion and this portion. So we want to match this prefix of length I is same as this prefix of length I here. So we can use the z value of this index. So we build this string t s plus reverse, and then find its g function. This is a function, you can copy paste it from somewhere now. And okay, then we also built another g function that I have explained in the second comparison. So what we are doing is we are trying all the prefix length from 0 to n. Now we are finding this, and this start is this start index. Okay, so this index will be simply what? This is 2n. This is the second string now. This index is 2n. This index is 2n, and we are skipping n minus I characters. So 2n plus n minus I plus 1, because if we are at I, this is not the length, this is the index. So if we are at I index, then I plus 1 characters are in the prefix. In the first part, first portion, I plus 1 characters. So n minus I plus 1 are in the later portion, this suffix portion, because this is necessarily the reverse suffix portion now, because this is a reverse of t. So we are subtracting n minus I plus 1, and if this z value of this start index, z value will give us the maximum length which is matching with the prefix. If z of start is less than I plus 1, then we simply continue, because we want that g of start has to be at least I plus 1. The first I plus 1 characters here should be same with the I plus 1 characters here. So if this is not, then we simply continue. Okay, next the second comparison. How we will do the second comparison? For this we build the string in this way, reverse plus s. So the reverse string will be like sn to si, then s1 to sn, reverse plus s, sn to s1 in reverse order, and then si to s1. Right, so this is in reverse order, and then we will append t, the original string t. This is not s, this is t. So the original string is starting by s0 to s1 to si characters, and then s1 to sn to s1, and this si plus 1 to s1. Okay, so if we are fixing I, then we know that the remaining suffix is this si plus 1 to n. So we want to compare this thing with this thing, this string, that this sn to si is the same as this string. So we are interested in this portion and this portion. So we will compare if this prefix, because with z function we can compare the prefix with some random substring. What z function allows us is to compare the prefix with some random substring. So with substring starting from somewhere. So we will compare this and the z value of here how it is this sn to s1. So sn to s1. So we will find the z value of this index. If the z value of this index is greater than or equal to n minus 1, n minus this value, whatever this, then this is matching with the prefix, and since this both are reversed, then we can directly match. The only issue we have is that the reverse issue, that's the main problem. So what we do is we again find the start. This is in this time this is the start index. So this is simply 2n, because from here the next string is starting. This index is 2n and we are skipping first I characters, so 2n plus I plus 1. And if this z2 is the second z function, if this value is less than n minus I plus 1, then we simply continue. Otherwise our answer is simple, because we know I, then we know that the next I characters in the given string t, the characters from I plus 1, the next I characters are the answer string t. So answer is substring from starting from I plus 1 of length n. S dot substring I plus 1 of length n, and we reverse the string because we know that the middle portion is in reverse order sn to s1. So reverse and print it, and print the I and return. This is the question. If you have any doubt, then leave the doubts in the comments. I will definitely answer them. Goodbye.